Thank you very much. It's a great pleasure to give this talk. And I should say that this is a joint work with two fantastic postdocs I have in ETH, Gishboliner and Tomon. And let me start with a setting which probably all you know, but this would be a motivation for what I say later. So imagine you have a subset of some group gamma, and you know that this set has small doubling, so means if you take A times A, the size of it is at most some constant times the size of A. And the famous kind of topic which people study in additive combinatorics, you want to know from here some information about structure of it. Right, so this is a kind of a setting. And then how you usually do it, so you start with example. So for example, if your group is a billion, let's say integers, then you observe that if A is a box, right, say some finite small number of dimensions, z to the d, then you know that A plus A is at most 2d to the d times A, right? And then you might guess, right, that's maybe a good point to start and say that any set, let's say, of integers which have this property, which has small doubling, looks in some sense like a box, and this is indeed true, right? I'm not saying anything very new, it's all well known. And this is a famous theorem of Frankl and Odlyzko, which says that indeed if A subset of integers such that A plus A has small doubling, right? Then there exists a generalized arithmetic progression, right? This stands for generalized arithmetic progression, which is essentially a projection of the box, generalized arithmetic progression P, such that A, say, subset of P, the size of P is not much bigger than the size of A, and P has small dimension. Right? And by dimension, it means it's a projection of the box in small dimensions. So that's a kind of a setting in additive combinatorics. So what I want to do today, I want to try and come up with some theorem like that for sets. Okay, so set systems. So I have a set system, right? So it's a collection of subsets of n element set. So first thing I need to do is to define what operation I'm going to look at. And one natural operation here, it's a taking intersection. So let me define by f times f is all possible intersection f intersection f prime, such that both f and f prime belong to f. And observe that here I allow you to take f prime to be equal to f. So in particular, right, my original set system is a subset of f prime set. Okay. And so now the question which I want to ask is the following. So suppose I told you that the size of f, right, and I put size in quotation because I need to define it, is approximately the size of f times f, right? So very similar setting to kind of Feynman's theorem. And I want from here to deduce something interesting about the structure of my set system. So that would be my question, which I want to address first. Okay? So to make it proper a mathematical question, let me first to define what I mean by size. So here's a definition. Right? So again, given a subset of, given a set family, subsets of n element set, I define you as vector space, right, which I denote by set. So this is a vector space, which is a span, right, span of all characteristic vectors of elements of F, right? And this is a characteristic vector. And it's clear what it is. It's a vector of length n, which has precisely ones on the elements which belong to it. Right? So this is my space. And then for size of S, size of F for me, right, would be a dimension of this space. Right? So that's how I will measure the size. Right? So give me a set system. I take all characteristic vectors. I take the span, let's say, over some field, F. It would be some finite field. It can be infinite field, but in this talk it would be some finite field. And then I measure the size of family by the dimension. And let me again repeat the question. So suppose I know that the dimension of space spanned by F is similar to the dimension of space spanned by F times F, right? So when I take all potential intersections, I don't go by much. What I can say about family F? So that's the question which I want to address. And obviously, exactly as in Feynman's theorem, you start with example, and then hopefully this example will lead you to correct answer, right? So here is again a definition of certain interesting class of the set system. So take your ground set and partition it to disjoint subsets, right, which I call atoms, right? AI is my atom. Right? And let S to be all to be unions of some sets AI. Right? So you take all unions, right? All possible 2 to the t unions of this set, right? So I call such S atomic, right? This S called atomic. Right? So again, I partition my ground set, and then my sets are only unions of these subsets. Now, obviously, if you have such family S, note that S times S is just equals to S, right? You don't have growth at all. And so one natural guess which you can have is that if you have a family F such that F times FF, very similar dimension to the original F, then you somehow close to be atomic. And this is indeed our first theorem. And to formalize it, let me give some definitions. So definition. So again, given a set family F, I define two elements in N to be twins if and then only if every F either has both ij or none of them. Okay. So basically, if you look on the vectors, characteristic vectors of sets F, in the coordinate I and the coordinate j, you always see the same number. It's either both zeros or both ones. Okay. So this is very well defined a notion. And moreover, you can see that being twins is equivalence relation. So therefore, I can partition my ground set, right, N, to the union of sets AI, where AI is a maximal set of twins, okay, which I, again, as I said, I call this atom. Right? So given any set family F, I can partition my ground set into subsets AI such that on every AI, I either contain it or not contain it. So every my family F lives in kind of an atomic family, right? And obviously, right, 0, 1 to the N is atomic family. It has precisely an atoms, but I can have much smaller atoms than that. And they need one more definition. So this is 1, this is 2, this is 3. And so the notation which I need that if you have some subset B of n, for me it would be kind of subsets of coordinates. Let's define a set system reduced to B. Its intersection of F with B for all F. Right? So you basically take a trace of your sets. Once I have all this definition, I'm ready to make this intuition that if you have dimension of F and dimension of F times F to be similar, then your F is close to the atomic. I can make it precise. And this is the first theorem which we have. Theorem 1. Which says the following: that suppose if right, you have a set system F and you have a dimension of the space spanned by F B and dimension of F times F. I always say times, but it's clear what I mean. It's this operation taking all possible intersections is D plus H. And I always think that for applications that my D is much bigger than H. So I take F times A and I don't go a lot in the dimension. So then the conclusion is that my set of indices, set of coordinates, set of elements can be partitioned into A1 union AD. Note that this is the same D as this D, right? So the number of blocks here, atoms, A1 up to AD, exactly as a dimension, plus some set B. So obviously AI are atoms of F, right? So F constant on every block AI. And the important thing is the dimension of a, if you take set system and you reduce it to B and you take a dimension, this is at most 2H. So this is a kind of a characterization of set systems with small doubling, right? Very similar in the spirit to Feynman, because right, you're not, if you have small doubling of integers, you're not equal to arithmetic progression, but you occupy a huge chunk of arithmetic progression. Actually, like Feynman's theorem is kind of huge, is not so huge, right? It's some percentage here, it's really pretty huge, right? So if your H is smaller than D, then you know that your set system has these D atoms, and because the size of this space, the dimension of this is pretty big, then here you have almost all possible, right, in terms of dimension, unions of these atoms, and on the rest of set B, you have a small dimension. Is this clear? Right? So this is a kind of the first theorem, right? You take set system, you take all possible intersection, you measure the size as a dimension of the space spanned by the set system. If your dimension doesn't go much, you're essentially atomic plus some set on which your set system has very few traces. Again, you measure this few in terms of the dimension. Okay. So this is the first theorem. I think it's reasonably interesting in its own right. It's kind of a natural characterization of set system with a small doubling, but we come up with this theorem not because we ask right away this question. We had some application in mind, right? We came to it through the application. So what is application? So application is a kind of a question which relates to very old seeming extremal set theory called Eventown problem, which was first proved by Berlekamp in the 60s. So what is the Eventown? So that set system F is Eventown. Right? It's called Eventown because he said a story about town and the clubs. I will not repeat it. So it's always called even town if the following two things happen. So every f in F has even size, and intersection of any two sets is even as well. And so Berlekamp was interested in this problem, and he proved in the 60s that if F is even town, then the maximal size such family can have is at most 2 to the n over 2. Actually 2 to the n over 2 even rounded down. And so let me tell you the proof. The proof is not very difficult. It's one of the early applications of algebraic methods in combinatorics. So what Berlekamp did, he observed that if you take a subspace spanned by characteristic vectors of elements of F, then this space is self-orthogonal with respect to the usual product, right? X dot y is sum of xi by I runs from 1 to n, and this is all modulo 2. Right? We do it over GF2. And obviously, since it's self-orthogonal, the dimension of the space plus dimension of the orthogonal complement can be of size at most n. So from here we'll get the dimension of V is at most n over 2 rounded down. And then there is another simple fact which you can prove is that if you have a vector space over GF2 of certain dimension D, that the number of binary vectors, which actually is a set in this, actually over GF2, it's not important, it's obvious, but I will use it also later. So even if instead of F2, I had here arbitrary field, if I have a vector space of certain dimension over arbitrary field, I will use it later. Then the number of binary vectors in this field is at most 2 to the d, right? So obviously in this case it's clear because the field has only 2 elements, but it's true in general as well. So this was Berlekamp's proof. And this is tight because, for example, if F is atomic and all atoms have size precisely 2, so there are n over 2 atoms, exactly right how we define atomic structure, and all atoms have size 2, then F has size 2 to the n over 2 rounded down. If n is even, it's precisely over 2. If n is odd, I throw away 1 element. And also the intersection, all sets have even size, and the intersection of any two sets is even as well. What is interesting to remark here is that this is not a unique extremal example, which many times happens in combinatorics. Actually, the linear algebra here is essential because it's not so easy to characterize all families which are even term. There are many, many of them. Actually, you can prove that if you have some partial even term, maybe not of that size, right? You just have a collection of even sets such that all pairwise intersections are even, you can complete it, you can add to it more sets until the size becomes 2 to the n over 2 rounded down. So that way you get many, many examples, right? So this is by far not a unique example. Very good. So once you have this even term result, one natural question which you can ask, what happens if you take this instead of even modulo some other number n, L. And so this is a question which was proposed by Frankl and Odlyzko. So Frankl natives. So they ask the following. Suppose I have a set system F such that F intersection F prime equals 0 mod L for every pair. Then, how large? What is the maximal size of it? Observe that again, you can take atomic system with every atom now has size L, and this will give the lower bound that your F can be of size at least 2 to the n over L rounded up. And so one natural question, is this an answer? It definitely is an answer when L equals to 2. So that's what Frankl and Odlyzko first asked. But then they find a construction using Adamar matrices that shows that there exists such F of size much larger, roughly 2 to the power constant log L divided by L times N, right? So by factor logging the exponent larger, and actually this is tight. This can be proved that this is tight. So this is based on an existence of Adamar matrices and direct product tensorialization. On the other hand, you can observe, this is another claim, that if F is intersection closed, and F equals 0 mod L for every F and F. So what I'm doing here, instead of looking only on pairwise intersection, I allow to put inside all possible intersections. So imagine I told you that all possible intersections, they're all divisible by L. Then it's clear that all atoms have size 0 mod L. Because you take a minimal set in F, and then because it's minimal, everybody either contains it or disjoint from it, and he has size divisible by L, so you can delete it and you can continue. And you show that all atoms for this set family have size 0 mod L, and therefore your family is indeed of size at most 2 to the n over, right? Because, right, so that was observation, that's kind of easy observation which one can make. And I think because of that, obviously I cannot know for sure, but I think because of this, Frankl and Odlyzko conjecture the following, that they said that for every L, there exists K constant, which depends on L, such that if K-wise intersection, so Fi1 intersection Fik, the size of all K-wise intersection is 0 mod L, Fij belongs to F, right? So if you look on all K-wise intersection, if they all divisible by L, so they conjectured, then you have this conclusion. Then the size of your set system is at most 2 to the 1 plus legal or 1 times n over. Right? So here they were pretty cautious, right? So they just said, even prove it asymptotic. So that was their conjecture. So actually I need to say that in their conjecture was slightly bit harder than what I'm going to consider today. So they wanted K-wise intersections to be divisible by L for different F elements, different K elements. What I'm going to deal all the time, I will allow you to some of these elements to be the same. So we have in a paper a reduction which allows to move from one problem to another. But for today's talk, when I say k-wise intersection, I mean intersection of k sets from F, they might be repeated. So in particular, exactly like when I define F times F contain F, 3 times F, it's all 3-wise intersections. It's contain F times F and contains F itself and so on. It would be a bit easier. So let me call such set system to be short k-wise l-divisible. So what they said that there is such a case such that if you have k-wise l-divisible system, then its size already at most 2 to the n over l, so you cannot have such an example. And that was our motivation, and that's why we got this theorem 1, right? So I leave it here. So the second result, or if you want the first result, because that was our motivation, is we proved this Frankl-Odlyzko conjecture, actually in a very strong form. So here's the theorem 2. Which says the following: so for every L, there exists K L, such that if my set family F is k-wise L-divisible, which exactly means all k-wise intersection of any k sets in F has size divisible by L, then the size of F is at most 2 to the n over L rounded down without any error. And moreover, we have a stability result here. If you tell me that your F bigger than 1/2 of this number, right, more than half of the extremal number, then all atoms of F divisible. Oh, actually, they have size. So then F really is subset of this atomic structure. So you have n over L atoms of size L. You take all possible their unions, and F lives inside there and occupies more than half. Right? And because it's more than half, you really need all atoms to be of size precisely L, otherwise you don't have space. So these are the two results which I wanted to mention. So maybe before I proceed with the talk, it's a good place to stop and ask for questions. So are there any questions? Okay.
How tight is theorem 1?
So, I mean, apart from this two, I think, right, you need to have an error term, and if I'm not mistaken, like it would be, it would be linear in H, but actually, I'm not sure we wrote any example in the paper. It's actually a good question. Maybe we should. I need to check. Any more questions? So let me give
Benny,
some proofs. So let me, for example, show you how theorem 2 will kind of follow from theorem 1. It will give you some ideas of why, right, why this is a kind of a right statement to prove here. And then maybe if you have more questions, I can say more things. For simplicity, I will choose the most cleanest case when L is a prime, right? So obviously not necessarily 2, but it would be easier for me to assume that my L is P is prime. Right, so I also assume that my F is not reducible, which means for every element I, there exists F containing I. Right, so I don't have elements which nobody contains. Obviously, it's a absolutely valid assumption. Otherwise, right, I just delete it and use the theorem for smaller L. And I also assume that, again, in order to save time, I will shorten this notion of K-wise l-divisible even further. Right, we're only talking about P being prime. So therefore, I call this thing Fk closed. Right? Which means that if you take F to the I, right, which we know what it is, it's F times F times F, like you take I wise intersection I times, and your I is less or equal than K, then all sets in F to the I divisible, have size divisible by P. So they all have size divisible by P. And moreover, just again to fix a notation, right, we said that given a family, it immediately determines the partition of the ground set into atoms, right? AI is atom of F is the I less or equal to K. It's very easy to see that this atomic structure is the same structure for all powers of A, right? So once I have a certain block, once I start taking an intersection, even for intersection, I either contain it or I do not contain it. And so therefore it's the same atomic structure all the way through. Okay, so this is my starting point. So the proof would be by induction, right? So I will show you just what that in this situation, one of this atom has size divisible by P, and then I can delete it and use an induction. Now, one remark is in place why I can use an induction. So my K would be reasonably large, not huge, but it would be exponential in P. And so one easy observation is to make that if your N is smaller than K, so you allow yourself to intersect sets K times. So if your N is smaller than K, that every atom which you have here can be represented as an intersection of at most N sets. And if N is smaller than K, that means of at most K sets. And therefore, by my condition that this F is K closed, means that every atom is divisible by P, and then I'm done. Right? So I have certain N, which is actually, if I assume my K is exponential in P, which is exponential in P from which I can start. This is clear, so I indeed can use induction. Right? For small n, just I know that all atoms by my condition are divisible by P. Okay, before we proceed, I need two simple lemmas. The first lemma is kind of a slight extension of this fact that self-orthogonal space can have dimension at most n over 2. So here's the lemma. So this is lemma 1. So he says, suppose I have a bilinear form on Fp and cos Fp and right? Which works like that. So B dw is sum of Bi Wi, I runs for 1 up to, and where these are coordinates, right? Where V is V1 up to Vn, and W is W1 up to W. And suppose I told you that z is the number of these coefficients bi which are not equal to 0, right? This would be my measure. And obviously, if all bi's are equal to 0, this form is identically 0, so I cannot say anything interesting. But suppose z is a number of bi's is not equal to 0, and V is some subspace of Fp to the n, such that the form vanishes on this subspace. B x y equals to 0 for every x, y, b. So then I want to deduce that the dimension of V, right, if all bi's were not 0, like before, like the usual scalar product, right, imagine they all were 1, I would write that the dimension is at most n over 2. So now I will have a correction. So dimension would be at most n plus 0. And again, just to be self-contained, it's very simple lemma. I prove it. So you take a linear transformation from Fpn to Fpn, right? Such that T of say V is a new vector B1, B1, and so on, B and V. Then you observe that the dimension of the kernel, actually, sorry, Z is a number of bi's which are equal to 0. So the dimension of the kernel of T is precisely Z, because it precisely makes Z coordinates to vanish. Right? And now if you take W to be an image of T, you observe that W is orthogonal in our usual kind of scalar product, which I define to be. So this is right from this definition of T and the definition of my right, because the product of W with any vectors in V is precisely this bilinear form on the pair. And from here I know that the dimension of W plus dimension of V is at most n. But because the kernel of T has Z, I know that also the dimension of W is at least dimension of V minus Z, because that's how much I can lose. So when you put it here and you deduce that dimension of V is at most n plus 0. So this is the first simple lemma. So now I need another lemma, and before I write it, let me remind you, right? So it's actually the same definition for vector spaces which I have for such system. So I have an operation of a vector space, which is I call product, but this would be not a product in any usual sense. So I define what is V times V, right? It's a new vector space such that all its elements would be U dot W, where U is in vector in V and W is in vector in V. And what is this U dot W? So U dot W, it's a vector whose coordinates just coordinate products of coordinates of U and W. So it's U1, W1, U2, W2, and so on, UN, WN. But imagine if this would have been sets, it's precisely the intersection of these sets. Right? But I can define this for vectors as well. So I just want to define this notation because this would be important what I could say next. So I call V K closed. Right? It's very similar to this K closed here. If for every U belonging to V to the I, right, I take all powers of V where I is at most K, I have that some of the coordinates of Ui right? So if you think that U is U1 up to UN, so sum of coordinates of UI from 1 up to n is 0. And just to have a notation for this, let's call some of the coordinates of UI kind of this norm of UI. Right? This is not norm in any usual sense, just some of the coordinates, right? Just a notation. So again, so product of vector spaces, just take a coordinate-wise product, and this gives me new vectors. And if I know that if you take a product of your space with itself up to k times, that some of the coordinates of the vectors which you get will be sum up to 0, then I can call such a space k closed. And my second lemma, right, we talk about k closed, two closed vector space. Actually, maybe I leave theorem 1 here because I'm going to quote it, so it's good for you to have it. It's not a problem, it occupies in space. So the second lemma, which I'm going to prove, is the following. So this is lemma 2. So think you have a subspace of Fp to the n. And you know that V is too closed. So which means that if you take any vector from V with product any other vector V, coordinate-wise, right? So this sum of these numbers is 0. Also, right, suppose that you took your set of coordinates and you partition it into atoms with respect, like what's called twin partition or atom partition for V. Okay? So what it means that every vector in V has the same value on A1 and same value on A2, the same value of A2. So you have this. Then you assume if the dimension, and suppose, right, so you have, this is twin partition, and now you look on the dimension of V, and imagine that the dimension of V is D minus H, where again, I think this is the same D, it's very important, right? And H is some number smaller than D. So then the conclusion which I'm going to deduce from here, then at least D minus 2H of the sizes of these blocks are divisible by now you kind of see where I'm going, because that's a very useful fact, right? So then, if, for example, this V came from the set system, right? So these twins are exactly the same twins which was atom partition, right? Of or twins or atoms, right? This is the same thing for my set system, and then I know that my set system has an atom, right? If D is bigger than H, then it will have an atom divisible. So again, this is not a complicated lemma, right? So let me call it to you. So again, we consider a mapping from Fp to the n to Fp to the d, where T of V is W, right? And what I assign, so W is a vector, W1 up to WD, such that Wi is a value S, and this value S is a value which V has on the block A. Right? So you look, right? We said every vector in space V, right? Actually, maybe I do it not from Pn, I do it only from V. I make only V to have P to the D. And then I know that every vector in V, it takes the same value on every block. So I take the image of V, the short vector of length D, which precisely records me these values. And so again, I'll define U to be the image of T. Now note that T is injection, right? So T is injection. So this T, right? Nothing goes, no trivial vector goes to 0. So in particular, dimension of U is dimension of V is V minus H. And now observe that, right, I can use lemma 1 because what happens if I take any two vectors from V and I multiply them, right? And I take, right, so let's, you know, X and Y would be two vectors in V, and I look on the vector X dot Y, right? You remember this vector have coordinates X1, Y1, and so on, X and Y. If I sum up all these coordinates, right, I denote this by norm of this new vector X1, and I know that my space is too close. So I know that these guys, some of these guys should be 0, right? So I know that when I take V times V, I get a new space whose for every vector sum of the coordinates equals to 0. Then I can think about this as some bilinear form over the vector Tx and Ty, as the image of X and image of Y, because if you look on this sum, that basically on A1, these guys would be exactly the same, right? And they would be repeated precisely A1 times, right? So my B is just my B of, I don't know, some more names, Z Q is precisely sum of BI, ZI, QI. I runs from 1 up to D, and this BI is precisely the size of the block, right? Because the sum of these guys, it's split into precisely D subsums, and every subsum is the same. So I have this BI here, which BI is the size of the blocks. And now, if you remember lemma 1, so lemma 1 says that if you will have few of these BIs which are 0 mod P, right? So only few of these BIs are 0, then your U should have size dimension roughly half of D, but actually it have almost full D. So you put these things together, right, and you get the result. So let me kind of. So let Z be the number of BIs, which is the size of AI, which is 0 mod P. Right? So then I know that, that because, right, I have B equals to 0 over this U, space U, right? This is exactly what is written here, because Tx and Ty, Tx and Ty, two vectors, general vectors in U. So because B equals 0 over space U, I have that the dimension of U is at most D plus Z over 2. But I know what the dimension of U. Dimension of U is original dimension of V. So I know that this is D minus H. So taking these things together, I get that my Z is at least D minus 2H. So I know that most of these blocks are divisible by P. So these are two lemmas. which I need. And now I can give you the idea why theorem 1 implies theorem 2, and it's any questions, by the way. And it's against kind of a usual tricks, which I think used quite a lot also in additive combinatorics. And so maybe let me delete all this, keep this lemmas, try to space goes down and down, but I think I'll manage, right? So I want to show you proof of theorem 2 using theorem 1. So first of all, again, let me remind you the setting. So I have a prime P, and I have my F to be K closed, right? Which means the sets in F, all their K-wise intersections are all divisible by P. And I take my K to be exponential in P. Actually, I think I need 2 to the 5 P, you'll see. I also suppose that this family F is pretty large, so it has size bigger than 2 to the n over P minus 1. Because I will prove you right away the stability version. So because my family is big, you remember I told you, right, that if you have a vector space of dimension D over GFP, the number of binary vectors in this space is at most 2 to the D. So from here I know that the dimension of a space of characteristic vectors of F should be at least n over P, right? It should be bigger than n over P minus 1. And now I'll do the following, right? I consider the following set system. So I start with F, and this would be my F1. And then my F2 would be just F dot F. And I continue doing so. So my Fi plus 1 would be Fi dot Fi. Which effectively just to kind of, because of the definition, I'll write it in the brackets, it's like F to the 2 to the I. Right? That's what it is. And because of that, I claim that there is index I such that if you move from here to here, the dimension cannot grow, because the dimension cannot be more than n, right? You obviously, all this set system live in Fp to the n, right? So therefore, there is an index I such that dimension of Fi plus 1, which is equals dimension Fi times Fi, is at most dimension of Fi plus say n over 5. Okay. And now you see why I need my k to be exponential, because I want to say that all these guys, which I'm going to get on the way, all these Fi's, right? I wanted to say all Fi's are at least 2 close, right? So if I take it close, if I take intersection of sets inside Fi, the intersections have still size 0 mod P, right? And because Fi is F to the 2 to the I, and I want this number to be smaller than K, right? And I do this obviously at most 5P times, you see how all numbers are related to each other, right? And now we're quite done, right? I'll briefly tell you why we're done, right? So you remember, right? So I have this atomic structure for F, but maybe before I write it, so I have this set system such that, or this vector space, such that when I take its product with itself, it doesn't grow by much, right? So let me take my H to be n over 5. P. And then I use this theorem, right? I have F of dimension D, and right, so D would be the dimension of this guy, so this would be D. Right, I have set system of dimension D, such that F times F is at most D plus H. So I know that I can split my ground set to A1 union A, right? So D is this dimension, plus some P. Right? I know that because my set system only goes, this D is at least dimension of this thing, so I know that D is at least n over P, that's also n over P, that's I also know. Right? And I know that the dimension of Fi reduced to B is at most H. So this is immediately from the theorem, right? Because Fi has small doubling, I know that I got an atomic structure, and I know that this dimension is at most reduced to Fi is to B. So let me take V to be the subspace spanned by the characteristic vectors of Fi, right? And I want to take, now look on V prime subset of V such that V prime is vanishing or is identically zero, is zero on coordinates in B. Okay? So because the whole subspace has dimension B, and the reduction of the subspace to this coordinates has dimension at most to H, if I take a maximal subspace which identically zero on B, I get that the dimension of V prime is at least D minus 2H. And also observe that V prime is still too close, right? Because my original V was too close. So if I took a product of the vectors, two vectors, and I sum up their coordinates, it was zero. Since V prime subset of V, it's also too close. Now we're exactly in the situation of lemma 2. Right? We have a subspace which is too closed, whose dimension is D minus H, and who lives only on A1 up to AD, exactly like here. Right? Because B is now not relevant. It vanishes on B. I can delete this coordinates. So because of that, right? So this subspace, right? V prime lives on A1 union AD. So because of that, by lemma 2, where you use 2H instead of H, you get that at least D minus 4H blocks AI are divisible by P, 0 mod P. Right? But you remember your D was n over P, H was n over 5P, so this is really a positive number. So in particular, you have one block divisible by P. And that's what I wanted. Then you delete it and use induction. Okay? So one remark which I want to finish with, so this proof shows that K, the number of intersections you need to require to be divisible by P, we can make it at most exponential in P. On the other hand, we have an example which shows that this K should depend on P. It should be at least logarithmic in P. It would be interesting to see where the truth is. Obviously, it should not be exponential, but what is kind of a correct answer, I currently have no guess. And so let me stop here.